And we are here. This is the video in this playlist, which really comes right after 10.7 Matrix Math Part 2. This is Matrix Math Part 3, where I am finally going to look at... Oh, I can't hear it. Matrix multiplication, or really I should say, matrix multiplication. Okay, so if you recall, what I'm doing, I know I look quite different, but I already covered that. The previous one was made a while ago. Anyway, if I have a matrix, right, and what I mean by a matrix is a grid of values. And let's say I have one that looks like this. A, B, C, D, E, F. This is a 3, no. It is a 2 by 3 matrix. We always refer to the number of rows before the number of columns. Now, what does it mean? And previously with, when I made some videos just about vectors, I talked about this thing called the dot product. But I'm going to change that here and write the matrix product. So first of all, what does it mean to multiply a matrix by something? I could just multiply this matrix by a single number. And that's what's known as, well, it's not really, that's what's known as scalar, sorry. Scalar. If I multiply this by a single number, then I just say, if this was a whole bunch of 1s, multiply it by 2, I got a whole bunch of 2s. You know, if I multiply by 2, double every value in the matrix. And I think actually now I did that in the previous video. I could also do what's known as element-wise multiplication. And that is also referred to as the Hadamard. I don't know if I'm pronouncing that correctly. And breaking news, somebody in the live chat that's going on right now told me that it also is sometimes called a Shor product. And what that means is, imagine I have another matrix that's exactly the same size as this one. And in fact, I could kind of do that a little small over here, and I could say, G, H, I, J, K, L, right? So I could have another matrix that's exactly the same size, and if I multiply these together, I have a new matrix which has A times G, B times H, C times I, D times J. Element-wise, each element of the matrix gets multiplied by its corresponding other element. Now, those are perfectly valid, I'm looking for my eraser, perfectly valid ways of doing multiplication. Oops, I don't need to. But what I'm really interested in is the matrix product. And the reason why I'm interested in the matrix product is because I want to use the matrix product for a neural network. For example, this node in a neural network is going to be the result of the weighted sum of all of the input nodes multiplied by weighted connections. And this one is also going to be the weighted sum of all of the input nodes multiplied by weighted connections, and so on and so forth. And so these weights are stored in a matrix. And the inputs come in a matrix as well. So if this is how I'm representing the inputs, then you might discover that I have this matrix of all these weights that I need to multiply those inputs by to get the new values of the outputs of this hidden layer. Now anyway, I kind of talked about that in a previous video, and I'm going to talk about it a lot more in the next video when we look at this in more detail. But the point here is that this idea of a matrix product is something that I'm going to need. Don't worry about the whole neural network thing. I'm going to come back to that in next video and go through that in detail. What I need to do here is just understand, I know I need the matrix product. How does it work? And then we'll see how it's applied in the neural network example. Okay, so let's say that I have a matrix A and I have another matrix B. And that matrix is equal to G, H, I, J, K, L. I'm writing the L like that so that I can see that it's not a 1 or whatever. Okay? So I have these two matrices. The way that I write the expression A matrix product B, I'm going to write it like this. A dot B. The dot as the indicator for the matrix product. Now, couple things that are really important here. One, the commutative property does not hold. A dot B does not equal B dot A. This is not true. And you're going to see why in a minute. You know, if I were to say 3 times 4, that's equal to 4 times 3. They're both equal to 12. But again, this matrix product is a different kind of multiplication. This commutative property does not hold. So that's kind of key. Another thing that's really important is the matrix product is something you can only do if the sizes of the matrices match up. And what do I mean by that? Now, one thing you might have realized, like if I was doing, when I had that example of the Hadamard product, that's only going to work if I have two matrices with the same exact dimensions, right? Because if I don't have the same exact dimensions, how can I multiply each element by the other element? Because some elements might not exist in one of them. But something even completely different is going to go on here. I need to have, for this to be valid, I need to have the columns, right? The columns of A equal to the rows of B. And you'll notice I made these do that. So I have to have, however many columns I have here, 3, I have to have exactly the same number of rows in B. Otherwise, this won't work. And the reason is, what I'm actually going to do is, the reason why I use this dot here is I'm going to use the vector dot product. Vector dot product. So you might have to go back to one of my previous videos where I talked about the vector dot product. Of course, I'm going to do it here again. But what the vector dot product does is it takes kind of like the sum of all the elements multiplied, the element-wise elements multiplied to each other. What do I mean by that? So if I say A dot B, I'm going to get, when I take one matrix, the A matrix product B, the result is also going to be a matrix. Now, how do I know the dimensions of that matrix? It's going to have the number of rows of A, which is how many? 2, followed by the number of columns of B, 2. So in the end, I'm going to get a 2 by 2 matrix. Now, this is going to be different with all different matrix dimensions. And after you watch this video, you can make up lots of different matrices and play a game with yourself to like do this matrix product with pencil and paper. And boy, won't that be fun. I'm going to go do that later myself, I'm sure. But here we can see I'm going to get a square 2 by 2 matrix. Now, what am I doing here? How do I fill in each of these blanks? So I'm going to just put a little blank square here. I know I need 2 by 2. Well, what I do is I take the dot product of the row of the first one with the row of A with the column of B. Right? So it's almost kind of like the intersection. This first element, right? I got to get the first row of A and the first column of B. That's why they have to have the same number of rows in B as columns in A. So what this actually is, this value here, is the dot product of these two vectors, which is, actually, let me just come over here, which is A times G plus B times I plus C times I. Okay, so that's this element here. Now, let's do this element here. Well, I'm in row 1. So I stay with row 1 of A, but now I'm in column 2, so I go to column 2 of B. So now this particular value is A times H plus B times J plus C times L. Okay? Ha! That's good. Now let me do this one. This one is the second row times the first row, the first column of B. D times G plus E times I plus F times K. And then this one here is going to be the second row times the second column. D times H plus E times J plus F times L. Okay? So that's the math. For any arbitrary set of matrices, you take the dot product of all the rows with the columns to fill out your resulting matrix product, and you must have the same number of columns in A as rows of B. Okay, so pause this video if you want, try to draw some diagrams, Google matrix product, Google image search matrix product, you'll probably come up with a million visual examples of this. Watch 3 Blue, 1 Brown's videos on linear algebra, which will probably teach this in a much more intuitive and nice way, but I'll link to that in this video's description. I'm now going to try to implement this matrix product in code. Minor correction, hopefully I said the right thing. But I do have something wrong here. A times G, B times I, C times K. This should be a K right here. Ta-da! Okay, so let's try to implement the math for this. So where I'm going to do this is in the multiply function. And I had written that before to do scalar multiplication. And I'm going to do the same thing I did in add, where I'm going to check what is the thing coming in. Is it a matrix or is it a scalar or etc. So I'm not going to bother with the Hadamard product. I'll add that into this matrix library if I ever need it. But I'm just going to check, is n an instance of a matrix? If that's so, then I want to do matrix product. Otherwise, I want to do scalar product. Okay? So now I need to write the code for the matrix product right there. But first, I must check, are the columns of A equal to the rows of B? Otherwise, I cannot perform the matrix product at all. So I'm going to come over here and I'm going to say, if, I'm in the right screen, yes, if the A is this matrix object, if this dot rows, no, if this dot columns does not equal n dot rows, I kind of don't like that this is called n here, but whatever. Then, and I'll use this more strict equals here, then I need to return like undefined or something. Like, just get out of here. This is no good. And I'm going to console.log columns of A must match rows of B. Columns. Now, I could be more thoughtful and I could use a try catch and some error handling, but I'm just going to do this for right now. Just to be some, and let's actually make sure this works. So if I go back to loading that code and I said something like A is a matrix that is 3 by 3 and B is a matrix that is 5 by 10. If I say A multiply B, I get undefined and it says columns of A must match rows of B. So that's working. And I could just say B is a matrix of 3 by 3 also. Then they match, and I would say A multiply B. I still get undefined because I haven't done it yet, but I don't get that error message. Okay, so now I need to create a new matrix. So I'm going to say the result is a new matrix that has the number of, what did I say? It has the number of rows of A and the number of columns of B. So it has the number of rows of A and the number of columns of B. Come on. Adam keeps wanting me to put my password in. Okay. All right, so that's good. Now I need to do each spot. So for each row, whoops, for each row and for each column, I need to do the dot product of, oh, whoops. First of all, I have an error. Before I can do this, I have an error here. And what I want is, if I'm at 0, 0, I want all of the values, I want to do the sum of all of the values. Whoa. So I want, let's just do this manually. In this case, it would be this dot matrix I times n dot matrix J. Well, sorry, I need another double nested loop in here, right? Because I'm going to take this and add I plus 1, but staying in J plus 1, right? Is this right? I plus 2, J plus 2. I mean, this isn't, I'm making this up because I'm doing this in an arbitrary way. We don't know what the actual rows, this just goes up depending on the number of rows columns there are. All right, right? So maybe I only need one loop here, because I need one loop. So what's that? No, because these could be different. Yeah. K. Weekman is telling me in the chat, another way of thinking about this is I could say, and you know what might be nice, actually? One thing that I could do here, just at least, I think this is going to help me work this out, is I could say let A equal this dot matrix, and let B equal N. Just to have variables called A and B for the two different matrices. And this is still the result. But in other words, what I'm saying is A, and this is B. So A, I, K, B, K, J. So, so hold on, let me, with K, sum over K. So hold on. So let me put this here. Did I get this wrong? This is B. Is it, yeah, so you know what's wrong about this? So let's look, now we can get this, right? Here's what I'm doing here. I want A, I want to be increasing not the row, but the column. Ah, I did it wrong. I did it backwards. Do you guys like watching these videos where I try to figure it out? I don't know. I could just get it right the first time. I could just like start over and get it right. But what I'm doing is every column of A, which column is, I'm actually using, yes, it's row I, but I'm iterating over the columns. Of course, of course, of course. So it is this. J, so this is what I need. So what I should be able to say is result, I need another loop for let K equals 0, K is less than, and I could use, remember I could use A's columns or B's rows. Those have to be the same. So I'm going to use A's columns. Is that right? Yes. K plus plus. And then first I need to say let sum equal 0. And then I'm going to say sum plus equal A, index I, K, plus B, index K, J. This, I think, is right. And then I have to put that in the result. Result I, J equals sum. So if I was using like some other vector library, I could like pull those out, then do the dot product. But let's see here. Let's make sure this is right. I want to, for every element in the result, I want to sum the dot product of all of the column spots in A, that's K, with all of the row spots in B. And then I've got the result. And line 57, I'm seeing deep space in the chat says line 57, oh yes, sorry, this needs to be multiplied. So these get multiplied. I'm summing the product of all of those. Yes. And of course, there are much faster ways. I'm not looking for any efficiency here. I'm just trying to understand the algorithm and make sure I have something that works. Okay, so now I need one more curly bracket, and I think if I zoom back out here, I think I am done. This is the algorithm, right? I have a new matrix that is the size of, and this I should do this down here, the size of A's rows and B's columns. Then I go through it and I do the dot product of a vector of a row of A and a column of B, store that result. Okay, and B, yes, here's another mistake. B equals n dot matrix, right? Because the actual two-dimensional array is stored in a variable called matrix. It's not the object itself has the data inside a variable. Okay, so how are we going to test this? I actually have a sketch here. So I'm going to, that's a P5 sketch. I'm not going to use anything about P5. I'm going to have A be a new matrix that's 3 by 2. Sorry, 2 by 3. I'm going to say the same for B, which is 3 by 2. Then I'm going to say A dot randomize, B dot randomize, console.log A dot matrix, and console.log, and not dot log, dot table, B dot matrix. So let's take a look at that. Okay, so now I have two matrices. This is one, and they're with random values in them. So now I'm going to say, let C equal A dot multiply B. Oh, I didn't get anything there. Oh, I didn't console log it. Oh man, console table C dot matrix. Oh, I forgot about that part. Okay, here we go again. Shoot. All right. So what's this error? Sketch.js line 11. Cannot. Did I forget to return it? I forgot to return it, didn't I? Okay, you know what might be nice is if at the end of this I said return result. And this actually goes where? Here. Right? I gotta return that result. All right, let's try this again. No. Did I forget to hit save? Uh-oh. I'm being told, breaking news. The return is in this for loop. That's not good. Oh, right, because the return was in the for loop. That's terrible. And this says results, and it should say result. Okay, I'm feeling a little bit more confident now. What? Oh, my goodness. I'm completely losing my mind here. So it's very important to realize that result is the matrix object. The matrix object has this array called matrix, which actually stores the values. And there's no like set function or anything. So what I actually really need to put here is result.matrix, right, equals this. Result.matrix equals, oh no, and then return result, right? So these values that I'm calculating, there probably should be like a set function or something like that. And I probably should have just created the 2D array here and then made a matrix, but whatever. This is what it needs to be. I think we've got it now. Oh boy. Okay, wait. Oh, this is the worst. I'm really doing a horrible, so I've done something terrible here. But hopefully, you're watching this video and maybe this is valuable to you. I have really conflated the idea of the 2D array that stores the values with the object. And I'm using it in all sorts of terrible ways. So let's think about this. This is what I want. A is this, B is N. Now I can get the rows and columns, but down here, I really need to say A dot matrix, B dot matrix, right? And that goes into the result dot matrix. So hopefully this is clear to you, the issue. But let me try to rephrase it again in case it's not. There is this idea of a matrix object. It has three properties: the number of rows, the number of columns, and the actual 2D array. So if I refer to the variable that's the matrix object and I want to actually do something to the data, I have to say the name of the object dot matrix. And I'm forgetting to do that in so many different places. So what I'm going to look at down here is I think now everything is correct. If A and B are the names of the objects, I can pull out the rows and columns from A, and then I can pull out the values from A.matrix and B.matrix, and set the values in result.matrix. Okay. I shouldn't be confident. I really should not be confident. This is a terrible idea, but I'm confident. Okay, so we finally got three things. If this is A and this is B, this is A dot B. Anybody want to fact check from me for this? Somebody in the chat. I'm gonna wait now. This will get edited out. Thank you, thank you. These numbers are in fact correct. I took a little break there and checked them. They are right. I encourage you to pause the video and check them yourself to see if you understand how the library is working. One thing that actually could be really useful, I don't ever employ tests ever, really, but I should learn about tests, and I should probably do some stuff with tests on this channel. So I think I might come back and try to do some tests that would, if I ever change the code for this matrix library, to ensure that the math still works. So anyway, maybe someday I'll come back and do that. Yes, there needs to be a lot of tidying up and refactoring. I can use these array functions, and I'm going to get to all that. But now we're ready. The next video, I can take this matrix library, this matrix class, and use it in my neural network class to perform the feed-forward algorithm of taking all these inputs, multiplying them by weights, and getting new outputs, which then go into other nodes. They become inputs to a hidden layer of nodes, et cetera, et cetera. So I've talked about that in the previous videos, and now I'm going to come back and actually do that. Simon in the chat makes a good point, where if you look at this class, all of these functions, randomize, add, multiply, well, up to multiply, they change the object that I'm calling the function on. So if I say matrix A, I say A.randomize, that matrix object actually changes. But with this matrix product, I'm not actually affecting the object. When I say A multiply B, I don't change the value of A. I create a new matrix object and return that value. So I probably should refactor the library to do maybe that matrix product in a slightly different way. And I could use something called a static method. So I'll come back maybe in a later video when I refactor this a little bit, but I wanted to mention that now. But it also reminded me there's one more matrix operation that I need for the neural network stuff. I think I don't actually need it for the feed forward, so I could come back and do it after that. But I do need it for the training aspect when I adjust and tune it based on what the guess is. Well, I get to all that later. The thing that I need is to transpose a matrix. So how do I transpose a matrix? If I have a matrix A with a certain number of rows and columns, the columns become the rows become the columns. So transposing this matrix would turn it into this matrix. Okay? So I'm going to quickly in the next video write a function that does exactly that.